In exercise 1 to 8, we need to determine which sets are bases for R3. Of the sets that are not bases, determine which ones are linearly independent and which ones span R3. Justify your answers. We know that any set is basis for R3 if they are if the columns or if the vectors are linearly independent and they are span R3. Now for the first one, since here we have a pivot in each column, that means the set are linearly independent. The columns are linearly independent. And since we have a pivot in each row, so this set is span R3. So from here we conclude the set is basis for R3. So the vectors are linearly independent. And the set is span R3. So from here we conclude it is a basis for R3. Basis. So now for 3 we have these 3 vectors. We need first to row reduce it because this one is already in the echelon form. So now we need to reduce this one. Let us write it as a matrix. So this, let us write here 1, here 3. So 1, 0, minus 2, 3, 2, minus 4, minus 3, minus 5, 1. If we do 2 row operation, row 3 is equal to row 1 plus row 3, and row 3 is equal minus row 2 plus row 3, we'll get the new matrix, which is 1, 0, 0, 3, 2, 0, and 3, minus 5, 0. It is clear here we have not every column is a pivot column, and we just only have 2 pivot row. That means it is not span R3 and the columns are not linearly independent. So from here we conclude it is not a basis for R3. So the set is linearly independent. So the set is linearly dependent because we have a free variable. Not span R3, no pivot in each row, or let us say row 3 does not contain a pivot, or not all 3 rows are pivot, has a pivot. So since both of them does not satisfy, it is not basis for R3. Now for the set in 5, it is here because it contains a 0 vector, so that means it is linearly dependent. So the set is linearly dependent. Here it contains 0 vector. For the span, we need to check if this one has 3 pivot. So let us write it as a matrix. Then we see if we need to do more row operation to check if we can have a pivot in each row. If we do 1 row operation, 3 row 1 plus row 2, we'll get the new matrix 1, 0, 0, minus 2, 3, 0, 0, 0, 0, 0, minus 3, 5. So here we have a pivot, here we have a pivot, here we have a pivot. So since we have 3 pivot, so every row has a pivot, that means it is span row 3. The set is span row 3. But since here it is linearly dependent, so the set is not basis for R3. Not a basis. Sorry. Because it is linearly dependent. Now for 7, so this is 5. Now for 7, since we have 2 columns, neither of them is multiple of the other, so the set is linearly independent. None of the vector is multiple of the other. Now for linearly dependent, linearly independent, we cannot, for the span R3, we cannot have 3 pivot rows since we have only 2 columns. So it is not span R3. So from here we conclude that the set is not a basis. Because it is not span R3. In 9, we need to find basis for the null space of the matrices. So to find the null space of the basis for the null space, first we need to reduce this one to echelon form. So 9, we have the matrix 1, 0, 3, 0, 1, minus 2, minus 3, minus 5, 1, 2, 4, minus 2. If we do row operation for this one, we need 2 row operation. Row 3 is equal minus row 3, row 1 plus row 3, and row 3 is equal to row 2 plus row 3, and we will have the matrix 1, 0, 0, then 0, 1, 2, then minus 3, minus 5, 0, 2, 4, 0. So from here we can write x as x1 is equal 3x3 minus 2x4, x2 is equal 5x3 minus 4x4, x3 is a free variable and x4 also is a free variable. So from here the bases will be the coefficients of x3 and the coefficient of x4, which are the free variable. So basis for null A is equal, now the coefficient of x3 is 3, 5, 1, 0. The coefficients of x4 minus 2, minus 4, 0, 1. So this is the basis for null A. Now let us see number 11. Find the basis for the set of vectors in R3 in the plane x plus 2y plus z is equal to 0. So in this one, if we write first x is equal, so we get x is equal minus 2y minus z. So that's mean our vector contain x, y, z, where x is minus 2y minus z, y is equal y, z is equal z. So now we have two free variables, which is y and z, which is equal y minus 2, 1, 0 plus for z minus 1, 0, 1. So this is written as this form. So now we can write the basis for null A will be this column and this column. So the basis for null A is equal minus 2, 1, 0 and minus 1, 0, 1. Similarly, for number 12, find a basis for the set vectors in R2 on the line y is equal 5x. So in 12 we have also the vector x is equal xy, where x is equal 5x, y is equal y. Sorry, where x is equal x and y is equal 5x. So x is equal x, y is equal 5x. So we can write this one as x multiplied by 1 and 5. So now the basis for null A is equal 1, 5. Then we have the last one, which is number 13 here from the set. So for 13, in exercise 13 and 14, assume that A is row equivalent to B, find basis for null A and call A. So here our matrix A, after row operations or row reduce this one, we get the matrix B. So first, to find the basis for null A, first we need to write x as x1 is equal minus 6x3 minus 5x4. For x2, it is equal half multiplied by 5x3 minus 3x4. x3 is equal x3 and x4 is equal x4. So now to write the basis for the null A, just we need to take the coefficients of x3 and x4 since they are free variables. So basis for null A coefficients of x3 is minus 6 minus 5 over 3 1 0. Coefficients of x4 is minus 5 minus 3 over 2 0 1. So this is the basis for null A. Now the basis for call A is all the pivot column. So here we have a pivot and here we have the pivot. So we need to take the column of A, which is the first one and the second one. Be careful here for the pivot, for the column, for the basis in call A, you need to take the column from the original matrix. So here minus 2, 2, minus 3, and the second one is 4, minus 6, 8. In exercise 15, find a basis for the space spanned by the given vectors v1 until v5. That means similarly if we ask find the basis for call A. So first we need to write this one as a matrix. Then we need to find what is the pivot column. And the pivot column will be the basis for this set of vector. 1, 6, 1 minus 3 minus 8, 7, 2, 1 minus 6, 9. So if we do row operation for this one, we get the final shape, which is 1, 0, minus 3, 0, 4, then 0, 1, minus 4, 0, minus 5, then 0, 0, 0, 1, minus 2, and last row 0, 0, 0, 0, 0. So from here it is clear that we have here a pivot, the first column, the second column pivot, then the third column pivot, the fourth column, sorry, pivot. So the basis for this set is equal the first column, which is 1, 0, minus 3, 2, then the second column 0, 1, 2, minus 3, and the fourth column, which is 1, minus 3, minus 8, 7. In 19 we have three vectors v1, 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 v2, v3, and H is equal span v1, v2, v3. It can be verified that 4v1 is plus 5v2 minus 3v3 is equal to 0. Use this information to find the basis for H. There is more than one answer. So if we can write here, we have this relation. So first, if we can write v1 in the form of v2 and v3, this will give us minus 5 over 4 v2 plus 3 over 4 v3. So from here the basis sorry for this handwriting. v2 and v3, which is 1, 9, minus 2, and 7, 11, 6. If we choose, for example, v2 is equal minus 4 over 5 v1 plus 3 over 5 v2. So here the basis will be equal to v1, v2, where v1 is this vector, v2 is this vector, sorry, v3, this one is not v2. v3. If we can write v2 in the terms of v1 and v3. Similarly, if we write v3 is equal to 4 over 3 v1 plus 5 over 3 v2. So from here it is clear that the basis is equal set of vector v1, v2. In exercise 21 and 22, mark each statement true or false. Justify each answer. So the first one, a single vector by itself is linearly dependent. We said this one is the zero vector is linearly dependent, so we cannot generalize this one. We said a single vector by itself is linearly dependent. So this one is false. The zero vector is linearly dependent. The zero vector is linearly dependent. For B, if H is equal span B1 until BB, then B1 until BB is a basis for H. This one we cannot say it is a basis unless it is linearly independent. So this one P is false. The set must be linearly independent. For C, the columns of an invertible n by n matrix form a basis for Rn. This one it is true because the invertible matrix is the columns are linearly independent and they are span Rn. So this one is true. D, a basis is a spanning set that is as large as possible. This one we said it is false. It is not as large as possible, it is as small. as possible. Now for E, in some cases, the linear dependence relation among the columns of a matrix can be affected by certain elementary row operations on the matrix. This one is false, because if the columns are linearly dependent, we do row operation, they still will be linearly dependent. So this one is E, this one is false. It does not affect. So now for 22A, a linearly independent set in a subspace H is a basis for H. This one false. We said also we need these to be coincide with H. So the set, sorry, this is A, it is false. The set must coincide with H also. Now for B, if a finite set S of non-zero vectors spans a vector space V, then some subset of S is a basis for V. This one is true. So B true, because it does not change. If we take a finite set, if we have a finite set of non-zero vector span a vector space V, then if we take a subset from this basis, if we take, sorry, a subset, so this subset will be a basis. So now for C, a basis is linearly independent set that it is as large as possible. This one is true. D, the standard method for producing a spanning set for null A described in section 4.2 sometimes fails to produce a basis for null A. No, it does not fail, because just we do row operation for the matrix AX is equal to 0, so we find what is the free variables, we take the coefficients of the free variables, so that will be the basis. So D is, this one is false, it does not fail. If in E, if B is an echelon form of a matrix A, then the pivot columns of B form a basis for code A. This one is false. We said the pivot columns of A form a basis for code A, not a pivot column of B. So this one should be A, not B. In 26, in the vector space of all real-valued functions, find the basis for the subspace spanned by sin t, sin 2t, sin t, cosine t. So we know that we can write sin 2t as half sin 2t is equal sin t cosine t. So since we can write sin t cosine t as half sin 2t, so that's mean if we take the set sin t sin 2t, there is no relation between these two, or this subspace is linearly independent, because we cannot write sin t in the form of sin 2t. Similarly, we cannot write sin 2t in the term of sin t only. So from here, the set sin t sin 2t spans the subspace. So by inspection, the set is linearly independent. So sin t sin 2t is a basis for a subspace. Because there is no relation between, we cannot write sin t in the term of sin 2t. Similarly, we cannot write sin 2t in the term of sin t only. But for sin t cosine t, we can rewrite it as half sin 2t. So now, just we will take sin t sin 2t, this form a basis for the subspace.